Good morning, students. Welcome to our physics class. The previous classes we have discussed about thermodynamics, thermodynamic system, thermodynamic variables, zeroth law of thermodynamics. Today we are going to learn internal energy and first law of thermodynamics. What is internal energy of a system? The internal energy of a thermodynamic system is the sum of kinetic and potential energies of all the molecules of the system with respect to the center of mass of the system. So what is internal energy? Internal energy of the thermodynamic system is the sum of kinetic and potential energies of all the molecules of the system with respect to the center of mass of the system. The kinetic energy. These energies are due to the molecular motion, that is translational motion, rotational motion and vibrational motions. These constitute internal kinetic energy. Okay. So the energy due to the molecular motions in translational, rotational and vibrational motion is called internal kinetic energy, EK. Potential energy. So the energy due to the molecular interaction is called potential energy. So it is denoted by EP, molecular interaction. For example, bond energy. So what is the total energy? Total energy of thermodynamic system is denoted by the symbol U. U is equal to EK plus EP. EK plus EP. That is sum of kinetic energy and potential energy. For ideal gases, it doesn't have any molecular interaction. Ideal gas molecules are assumed to have no interaction, so there is no potential energy. It consists of only the kinetic energy. Okay, so that depends on the temperature and number of particles. But this is not true for real gases. For ideal gases, there is no potential energy. Only the energy is due to kinetic energy. But for real gases, Van der Waals gases and all, this is not true. Also, we know that internal energy is a state variable. It depends upon the initial and final state of the thermodynamic system. Okay. Let's move on to the next topic. That is Joule's mechanical equivalent of heat. Joule's mechanical equivalent of heat. James Prescott Joule, he has shown that the mechanical equivalent of heat, that means the mechanical energy can be converted into internal energy and vice versa. Mechanical energy can be converted into internal energy. So this was explained by James Prescott Joule. Now let's see the experiment of this Joule's mechanical equivalent of heat. This experiment consists of a calorimeter which is made up of copper. And in this calorimeter, the liquid has filled. It is closed by means of a lid. In this lid, two holes are made. Through one hole, thermometer is inserted. And the other hole, the masses will be connected by means of a rope through pulley, and a paddle wheel is attached. That is, in this area, a paddle wheel is attached. There is a wheel here, okay? And there is a small drum. It is connected here, spring, and the spring, the top there is a handle. Okay, top there is a handle, and the masses will be connected by means of a pulley. So here the weight hanger is attached and the weight will be added. On this side also there is a weight hanger is attached by means of a pulley. Masses will be attached. The whole setup is kept, that is this copper calorimeter is kept in a well insulated container. Insulated container of water is filled, and this will be kept in a particular stand. Clear? So this is about the experimental setup. So there is a calorimeter made up of copper, and thermometer is inserted to measure the temperature, and there is a paddle wheel. Two masses will be attached by means of a rope through pulley, and which is connected to a spring. There is a handle at the end of this spring. So listen, the weight of this masses will be acting downward mg. Okay, so this we can consider as a height h, and here also we can consider if the weight acting downward direction mg, so this will be considered as a height h, measured height. How this height will be measured? When the mass falls, that is when these masses falls through a distance h, okay, because of gravity, when these masses falls through a distance h, this masses will be loses its potential energy. It loses or it lost its potential energy. So how many potential energy has lost? Here 1 mgh and here 1 mgh. So loss of potential energy is 2 mgh. When the mass falls, the potential energy of these two masses gets lost. That is equal to mgh. So when it falls, this paddle wheel turns. Okay, this paddle wheel turns. So there will be a connection with the liquid. So due to the turning of the wheel inside this water, there is a force. What force? Frictional force will be comes in between the water and the paddle wheel. Okay, when the mass falls, this paddle wheel gets turns, so that there is a frictional force exists between the water and the paddle wheel. What will happen? There is some work is done. It rises in the temperature of the water. So beginning we should measure the temperature of the water. After this work, when these masses falls, we can note down the rise in temperature of the water. So what you understand from this here, the loss in potential energy, that is gravitational potential energy, is converted into internal energy of the water. The water's internal energy gets increases. That means the temperature of the water increases due to the work done by the masses. So gravitational potential energy is converted into internal energy. Potential energy is a type of mechanical energy which is converted into internal energy. That is, the temperature of the water gets increases. Okay, so temperature of the water gets increases due to the work done by the masses. That is, Joule was able to show that mechanical work has converted into heat because of the masses fall. So mechanical work is done, which will be converted into internal energy. That means it raises the temperature of the water. So mechanical work, energy is converted into heat. So this is Joule's mechanical equivalent of heat. He also found the calculation. That is, he found that to raise 1 gram of an object by 1 degree Celsius, okay, to raise the temperature of 1 gram of an object by 1 degree Celsius, the energy required is equal to 4.186 joule. 4.186 joule of energy is required. Actually, this was measured in calorie in earlier days. The heat was measured in calorie. That is, 1 calorie is equal to 4.186 joule. So this is called Joule's mechanical equivalent of heat. Understand? So what he found? He found that to raise the temperature of 1 gram of an object by 1 degree Celsius, the energy required is 4.186 joule. Actually, this was called as a 1 calorie. 1 calorie is equal to 4.186 joule. So this is called Joule's mechanical equivalent of heat. The next topic is first law of thermodynamics. This first law of thermodynamics based on the law of conservation of energy. Law of conservation of energy. Actually, here the heat energy involves. Okay. So this law states that change in internal energy of the system is equal to heat supplied to the system minus the work done by the system. What is that? Change in internal energy of the system is equal to heat supplied to the system minus the work done by the system. So mathematically we can write delta U. Delta U is the change in internal energy. U represents the internal energy. So change in internal energy is equal to heat represented by Q, heat supplied to the system, minus work done by the system. W is the work done by the system. So this is about first law of thermodynamics. Understand? So the internal energy can be changed either by heating or by doing some work. Isn't it? How the internal energy can be changed? It can be done by some work, doing some work, or can be done by heating. So listen these points. When the heat flows into the system, the internal energy increases. When the heat flows out of the system, internal energy decreases. Understand? When the heat flows into the system, internal energy increases. When the heat flows out of the system, internal energy decreases. Similarly, if the work is done on the system, internal energy increases. The work is done by the system, internal energy decreases. So based on this, we can give the sign. Okay, sign convention can be introduced. For that, heat flows into the system means system gains heat. Am I right? System gains heat. So what will happen? The heat will be positive. The Q value will be positive. If the system gains heat, Q is positive. Heat flows out of the system means system loses heat. So that time the heat will be negative. Similarly, work is done on the system means W is negative. And work is done by the system means work done is positive. So these are the sign conventions. Look at this figure. Here, these two figures, the heat is supplied. Okay. So when the heat is supplied to the system, Q is, that is system gains heat, so Q is positive. Q is greater than 0. Similarly, the work done. What is work done? Here work is done by the system. So W is greater than 0. In this one, heat is supplied to the system. So obviously Q is greater than, so Q is positive, and there is a work done. By the work is done on the system. With hand some work is done on the system. So work done is negative. We are just adjusting the piston with the help of mechanical work, right? And these two cases, system loses heat. That's why there's an arrow mark here. System loses, so Q will be negative. Q is less than 0. And work is done on the system. So W is less than 0. Here, heat, system loses heat. So Q is negative and work is done by the system. There is no hand here. Work is done by the system. So work done is positive. Actually, this first law of thermodynamics can be applicable for solids, liquids as well as gases. Okay. Solids, liquids and gases, this first law of thermodynamics can be applied. The next topic is quasi-static process. Quasi-static process. Listen, it is actually a very slow process. Very slow process. In that each stage there is an equilibrium occurs. Okay, let's see that. Consider a system of an ideal gas kept in a cylinder of volume V at pressure P and temperature T. When the piston attached to the cylinder moves outward, the volume of the gas will change. As the result, temperature and pressure will also change. Because we know that ideal gas equation is PV is equal to NKT. So whenever there is a volume change, there will be changes in pressure and temperature also. Understand? So when the piston is attached to the cylinder, if it moves outward, volume will be changing automatically, pressure and temperature also will be changing. Now let's see, if a block of some mass is kept on the piston, it will suddenly push the piston downward. What will happen? The pressure near the piston will be larger than the other parts of the system. So it implies that gas is non-equilibrium state. Okay, immediately the pressure will be larger near the piston. So it is not in equilibrium state. That means the pressure temperature we cannot be determined properly till it reaches the equilibrium. But if the piston is pushed very slowly, such that at every stage it is still in equilibrium with the surroundings. Infinitely slow process, I said. Very slowly when the piston is pushed, each and every second, every stage is still in equilibrium with the surroundings. Understand? So this is known as quasi-static process. So define quasi-static process. A quasi-static process is an infinitely slow process in which the system changes its variables PVT so slowly such that it remains in thermal, mechanical and chemical equilibrium with its surrounding throughout. By this infinite slow variation, the system is always almost close to the equilibrium state. Understand? Infinitely slow process in which the system changes the variables pressure, volume, temperature so slowly such that it remains in thermal, mechanical and chemical equilibrium with its surroundings throughout. By this infinite slow variation, the system is always almost close to the equilibrium state. One of the example is given there, that is Consider a container of gas, volume V, pressure P and temperature T. If we add sand particles one by one slowly on the top of the piston, the piston will move inward very slowly. So this can be taken as almost a quasi-static process. Understand? The sand particles added very slowly, it will be giving the very slow movement of the piston downward. So it is considered as a quasi-static process. Let's see the work done in volume changes. So consider a container which is filled with gas. So a movable piston is placed or fixed in this container, a cylindrical container, and here a piston which is placed, movable piston. Suppose the gas may be expanded very slowly, quasi-statically, by the movement of piston to a small distance dx. That is, this is the container, gas is filled. This gas can be expanded. This gas can be expanded by means of the piston movement. By pushing the piston quasi-statically, very slowly, the gas gets expand. So, the small distance the piston may move, let us consider this as the dx distance. Okay? So, the expansion occurs quasi-statically. That means the pressure, temperature, internal energy will have the particular values at every second. Now, let's see the work done. So, small work done by the gas on the piston. The small work done by the gas on the piston can be written as dW, small work done. dW is equal to F into dx. So what is force exerted on the gas? Force exerted by the gas on the piston. Force exerted by the gas on the piston, F is equal to P into A. What is P? Pressure. A is the area of the piston. A is the area of the piston and P is the pressure exerted by the gas. So we can write dW is equal to, instead of F, PA dx. PA dx. So actually what is A dx? Area into distance is nothing but volume. So since it is dx, we can written as dV. Change in volume during this expansion process. Okay. So again the work done can be written as dW is equal to P into dV. So work done can be written as force in displacement. Force can be written as pressure into area. Here A is the area of the piston. P is the pressure exerted by the gas on the piston. Now dW can be written as PA dx. So A into dx, area in distance is nothing but volume. So that is change in volume in the during expansion process. So the small work done dW is equal to P into dV. Now here the positive value. So the volume is increased. So there is no negative, so positive is there. So the volume may be increased. Generally the work done by the gas, the volume is increased by means of VI to VF. There is a positive sign, we can consider the volume of the gas is increased. So the volume changes from VI to VF. So how can we calculate the work done by the gas? Integrate this equation. So integral of dW, integral is this symbol. Integral of dW is nothing but W. That is equal to integral of PdV. Limit is from VI to VF. Initial volume to final volume. Suppose if the work is done on the system, the work is done on the system means what is that? VI will be greater than VF. So W will be negative. Work done is negative. Okay. So this is about work done by the volume changes. Work done by the volume changes. Actually, here P is inside this integral. This need not be constant, isn't it? While doing some work, the pressure need not be constant. So first, when we are doing the problems, we should write the pressure in terms of a function of volume and temperature. Clear? Function of volume and temperature using the equation of state. If you are writing, we can substitute the value of P here. So it may not be a constant one. So this is about work done in volume changes. Okay. A gas which is expanded by means of the piston with a small distance dx. Small work done, force. So work done can be plus PA into dx. A into dx is nothing but volume. So P dV. So if the volume is increased, we can have VI to VF. So dW, integral of dW is equal to W is equal to VI to VF PdV. If it is positive. If it is negative, when it will be negative, the work is done on the system. When the work is done on the system, that means VI will be greater than VF. So the work done will be negative. Clear? The next one is PV diagram. PV diagram. That is, it is the graph between pressure and volume. It is the graph between pressure and volume. So this diagram we can use to calculate the work done. Using this PV diagram we can use to calculate the work done by the expansion or by the compression. Okay. So PV diagram, the volume will be taken along the x-axis and pressure will be taken along the y-axis. So work done by the gas during expansion. During expansion, suppose this is the initial pressure and initial volume position, Pi and Vi. So when the volume increases, the pressure may decrease. So this is Pf and Vf. Okay. Actually this curve depends upon the thermodynamic process. What process we are considering, the nature of that thermodynamic process, we will be getting the PV diagram. Okay. So how can we calculate work done? The area under this curve. The area under this curve is equal to the work done. So W is equal to integral of PdV. W is equal to integral of PdV. So this is about PV diagram. It is nothing but a graph between pressure and volume of the system. So with the help of this diagram we can calculate the work done. That is, if you are calculating the area, that is equal to the work done. So today we have discussed about internal energy, first law of thermodynamics, Joule's mechanical equivalent of heat, quasi-static process, work done in volume changes and PV diagram. Okay. So the questions you have to learn, define the internal energy of the system and define 1 calorie. Then did Joule convert the mechanical energy into heat energy? Explain. State the first law of thermodynamics. Then can we measure the temperature of the object by touching it? Give the sign conventions for Q and W. Define the quasi-static process. Give the expression for work done by the gas. And what is PV diagram. Then explain Joule's equivalent of heat, mechanical equivalent of heat, and derive the expression for work done in the volume change in the thermodynamic system. So learn these questions. Study well, students. Thank you.